So, expanded octets. First, the definition, I guess the most important part of this for you people. Some elements can have more than 8 electrons in their outer shell. It's a big deal. I guess it's really not that big of a deal, but it's kind of neat. Now, one little rule I'd like to mention for when we draw these out, which is nice, some of you will appreciate this. There's no double or triple bonds, at least in what we're doing. Oh, we all go yes. Okay. So, no double or triple bonds. Now, here's what we're going to do. We're going to do 2 of these. First one we're going to do is SF6. I already showed you like the skeleton structure before. We're going to actually draw it out correctly. So, sulfur hexafluoride. All right. So the way sulfur hexafluoride works, you need to figure out valence electrons and everything just like before. So you'll do sulfur. You've got 6 valence electrons. Fluorine, you have 7. How many do you have, though, obviously, of them? 6. You add that all up. What's it going to be?
48.
48. I think it's 48. Once you do this, what you're going to do next is draw out your skeleton structure. You put S in the middle. And then what we can do, we actually can bond all 6 fluorines to that S. Does that bring up questions for people? How many electrons did I just put in? 12. So you do 48 minus 12 equals 36. You know what? We'll keep going. Now, how many electrons do I have to add all around here? I've got 36 available. How many can each F hold? It can hold 8. How many more does it need? It needs 6 more. 6 times 6, 36.
No, that's
6 times 6 is 36. Just trust me on that one. I think I memorized that when I was like a little kid. Yeah, I know. So anyway, you fill that out like that. Now, you got everything's good. So it's kind of weird. Like, you have your Fs, they all have 8. Sulfur has 12, which I know is a little bit weird, you know. Now, like we described before, you think about this, you're going to have to identify hybridization now. And you're also going to have to identify domains and stuff. So, total electron domains for this element, or for this molecule. That's basically just asking how many electron pairs are around the central atom. How many? 1, 2, 3, 4, 5, 6 pairs, right? So 6 total electron domains. How many shared? All 6 are shared. How many unshared? 0. Simple as that. Now, if you were to figure out hybridization, I'm going to give you a chart in a second that's going to like make this incredibly easy, actually. But if you think about it, it's 1, 2, 3, 4, 5, 6. The hybridization will be sp3d2. You'll need that because your sp3 will hold 1, 2, 3, 4. So it'll hold 4 of the bonds. But then you also need to have d2 to hold the last 2. Okay? So now, XeF2. This is a noble gas. Have we ever dealt with it bonded in a compound before? No, we have not. We're going to now, though. Look at that. So you're going to treat this exactly the same as you would anything else, okay? You're just going to go Xe. It's got 8 valence electrons because it's a noble gas. Fluorine has 7, and you got 2 of them. So you add that all up, you get 22 electrons. Do we agree?
Yes.
Cool. Now, you take your Xe, you bond it to your 2 Fs like that. I just put in, so 22 minus 4, because remember, each bond is worth 2, 18's left over. So here's what you're going to do. This is the part where it becomes a little weird again, where it's expanded. You're going to fill in your dots around fluorine. I just put in 12. That leaves me with 6. Now, in doing this, xenon only has 4 electrons total to begin with. That's good. You've got 6 available. So what you'll do, you can put 2 here, you can put 2 here. I did move them off to the right for a reason, just so you know. So that leaves you with 2 left over, right? I just put in 2 and 4, so I got 2 left over. Now, here's what you'll do. Whenever you have 2 remaining like this, or whenever you have any remaining after creating something like this, assuming you did your math right, that means that it's an expanded octet. And what you're going to do is take those 2, and you can just put them on xenon as well. Because the way xenon works, it has those extra d sublevels, those extra d orbitals that can hold more electrons, and you get this. So if you now this is a good way to practice. So you can do total pairs, so you can do total domains. You can do shared, unshared. So how many total do I have on xenon? This is good practice. There's 5 total domains. 2 bonds, 3 electron pairs. So shared would be 2 shared bonds, and then unshared would be 1, 2, 3 pairs. Does anybody have questions on that so far? Seriously? To figure out your hybridization and your shape, you can look at your chart. You've got 5 total domains. You've got 2 shared, 3 unshared. Believe it or not, that makes it a linear atom, or pardon me, a linear molecule. Now here's the thing. There's a difference. There's molecular shape and there's electron geometry. Remember, we talked about this. In looking at this, remember that the molecular shape is they're the atoms. They're the balls around this. But then in looking at this, remember, it's the springs that represent the electron domains.
How do you know which springs to see then?
For the assignment you're going to do in general, you're going to be looking at the shape, the molecular shape, usually.
Okay, and then how do you know when you have to do hybridization?
So, well, what you're going to do is you'd say, okay, this is a linear molecule, and then the shape, you would look at, or pardon me, the hybridization, this chart just tells you it's nice, it's sp3d. But if you wanted to think about it, 5 domains means you would have S, 3 Ps, and 1 D to add up to 10 total electrons, if you want to think about it like that. But that's the general idea. Wait, stop.